Welcome back. Today, we'll be continuing Chapter 2, talking about measures of spread and center. We'll first talk about 3 different ways that we can measure the center of a set of numerical data. The first one is called the mean, and this is often known as the arithmetic mean or the average. We can calculate the mean by adding up all of the data values and then dividing by the sample size or the number of included data values. The second method is known as the median, which is sometimes called the center or the middle. The median is calculated by taking all of the data, putting it in order, and then selecting the center value. If there's an even number of data values, we will average the 2 center ones by taking the mean of them. Finally, we have the mode, which is simply the data value or values with the highest frequency. Whichever data value shows up the most will be the mode. If there are multiple data values that all have the same highest frequency, then we can call them all modes. And it is perfectly okay for there to be 2 or 3 or more modes. In general, the mean and the median will be more useful than the mode for discussing the center of a data set. Both of these measurements are going to end up being useful for different reasons. Before we talk about when we might care about these different measurements, let's first do an example to find them. So let's suppose that we have this given data set, and we want to find the mean, the median, and the mode for each. The first thing we'll need to do for the mean is count up how many data points there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can say little n is equal to 10. Little n is the variable that we use for the sample size. If this was the entire population, then we would use a capital N. You can assume, unless it states otherwise, that we're just dealing with a sample. For the mean, we will simply add up all of the data values and divide by the sample size. In this scenario, this first symbol here means take the sum of or add them all up. This is x, which represents the data. And as we mentioned before, n is the sample size. So in this scenario, we have 3 plus 4 plus 8 plus 8 plus 10 plus 11 plus 12 plus 12 plus 14 plus 15, all divided by 10. We can plug this into our calculator in order to find the final answer. In this case, the sum of all of the data values ends up being 97, which, when we divide by 10, gives us 9.7 as the mean. This is the average value for this data set. Up next, we can find the median. In order to find the median, we will put all the data in order. In this case, it's already in order for us. And then we will find the center value. The easiest way to do this when we have a data size this small is to just cross off on each end until there's either 1 or 2 left. If you get down to 1 data value, then that's our answer. If you get down to 2, then you'll have to take the average here. So in this case, we'll get 10.5 as the median. Finally, for mode, we simply count which data values have the highest frequency. Both 8 and 12 show up twice, and no other data value shows up 2 or more times. So 8 and 12 will be both of our modes. And it's perfectly okay that we have 2 modes here. The median and mean, as I mentioned, are the 2 most useful measures of center. The reason that we care about both of these things is that if there are extremely high or extremely low values, they will influence the mean because the average accounts for every number equally. But just a few extremely high or extremely low values will not affect the median. As a result, we will want to consider both the mean and the median in order to get a clear picture of what a data set looks like. If the mean is much higher than the median, for example, that might tell us that there are some very high data values in the set. And we'll come back and talk about that a little bit later on. For now, let's expand on the idea of the median by talking about percentiles. A percentile is the value where that percent of the data is less than or equal to the given value. So for example, we might say the 50th percentile would be the data point where half of the data is less than or equal to that value. The median is equal to the 50th percentile. 2 other percentiles of note are the 25th and 75th percentiles, which we will frequently call the first and third quartiles, or Q1 and Q3 for short. By noting the quartiles as well as the median, which can sometimes be called the second quartile, or Q2, it gives us a good sense of where the data breaks down into quarters of data, the first quarter, second, third, and fourth quarter. Therefore, we'll often look at a 5-number summary, which gives us the minimum, 3 quartiles, and then the maximum value for a data set. The interquartile range is one measure of how large our data set is, how spread out it is. It's the difference between the first and third quartile. We've talked about the range before, which is the difference between the highest and the lowest data value, but the interquartile range can often be more telling because it is not affected if there are just a few significantly high or significantly low data values. In particular, we will use the IQR, or interquartile range, to identify what's known as an outlier. An outlier would be a value that is significantly higher or lower than the rest of the data set. And for our purposes, we will say that a data value is an outlier if it is more than 1.5 times the IQR away from the middle 50% of the data. So in other words, we're looking to see if we are more than 1.5 times the IQR below the first quartile or the same distance above the third quartile. Let's go through an example here. We have a certain exam where these are the given test scores. We'll want to find the 5-number summary and identify any given outliers. Now, the first thing we'll need to do is put the data values in order. So let's take a look here. I see a 25.5, then nothing in the 30s. There's a 45, nothing in the 50s. Any 60s, there's a 65 and a 68. In the 70s, 78, 76, 79, 78, 79. Okay. So 76 is the smallest. Then I saw 2 78s and 2 79s. In the 80s, there's an 80, an 81, another 81, 83, 84.5, 85, 88 and 89, And then I see 90, 90, and 3/98. So the first thing we'll need to do is we'll need to find the median. When finding the median after we've ordered the set, if we're going to keep going, I like to do my crossouts under the data values rather than on top of them, because we'll need to be able to do a second set of crossouts for the IQR. So let's cross off from either side for the median underneath. Just crossing off one at a time from either end. Our data didn't fit in one row here, so I used 2 rows to make it easier. Okay, looks like we've got 2 81s in the middle, so our median will be 81. We can also very quickly, while we're here, identify the min and the max. So the median was 81, the minimum is 25.5, and the maximum is 98. Next, we can identify the quartiles. We'll draw a line right down the center of the data. If there was just a single number in the center for the median, we would exclude it on both sides. But because we were split down the middle with 2 numbers, we'll include each number on either side. And then we'll do some crossouts. So we can cross out here on the left to find the first quartile, 78. And on the right over here to find the third quartile, 89. Q1 and Q3 are 78 and 89. So this right here is the 5-number summary, and it gives us a sense of what's going on. We can often graph the 5-number summary is what's known as a box plot. You may have called this a box and whisker plot if you learned this when you were in elementary school, because it looks a little bit like it has whiskers coming off. The way that we'll make this graph, and we typically don't need it to be very nicely to scale, is we will draw a box, and at the ends of the box, we will have Q1 and Q3. So in this case, that's 78 and 89. Then the median will be drawn as a vertical line inside of the box. So in this case, that ends up being 81, which is much closer to 78 than it is to 89. It doesn't have to be perfectly to scale, but we want it to be roughly so. Then we will add whiskers coming off to the side as a line extending to the maximum and to the minimum, which in this case are 25.5 and 98. This does a really good job of giving us a visual picture of this data. In this case, it looks like 25% of the people scored right here in this very small range, and the next 25% of the people scored in this range. So half of people got basically a B or maybe a high C. In fact, it looks like 20% of people scored a B, and 25% of people scored a B, and 25% of people scored a C plus, basically. There's some 80s in there, some 81s right on the borderline, but that gives us a pretty clear picture. Then 25% of people scored basically an A, and 25% of people scored a C or below. So 75% of this class got a 78 or above. That's pretty good. That's a nice data set. I would say those are some scoring students. To find the IQR, which we will need to identify outliers, we will take Q3 minus Q1, which will be 89 minus 78, which is equal to 11. We'll need 1.5 times the IQR, which is 11 times 1.5, or 11 plus 5.5, so that'll be 16.5. We'll need to check for any data values that are above or below 1.5 IQR from that 50th percentile. So we will check on the bottom end for low outliers. 70, let's write it out first. Q1 minus 1.5 times the IQR would in this case be 78 minus 16.5. So that would end up being 62.5. We're looking to see if there are any data values below 62.5. And there are two, 45 and 25.5 are outliers. Two extraordinarily low data values compared to the rest of the class, which makes sense if you look at the data. Only two of these students failed, and the two that failed by 20 points more than the next lowest score. On the high end, we're looking for Q3 plus 1.5 times the IQR, which would be 89 plus 16.5. So that will be 105.5. Now, of course, there's no data scores above 105 for this exam. The highest I see is a 98. So there are no high outliers. Very frequently, we can mark outliers on our box plot by marking them separately with X's. And then we'll end the whisker on the lowest data value that's not an outlier. We can see that in this image, it now gives us a sense of what's going on. Oh, actually, almost 25% of the data was at or above a 65 to 78 for the first quartile. But there are two extremely low values that might make it look like our data is more spread out. Because while 25% of our data is between 25.5 and 78, it's only two very low values that are throwing it off. Most of the values are in this much smaller range. So we can mark our outliers with an X to indicate more clearly for visuals the spread of the data. Now that we know how to calculate lots of different types of measurements for a data set, we can talk about skewness. The skew of a graph is the direction in which the graph is leaning. And we can talk about the skewness of a data set or the skewness of a graph. Basically, a graph is skewed in the direction of its extreme values. You can think of this in terms of outliers, but we now have an official way to talk about outliers. So we can't say outlier because sometimes extreme values that don't classify as outliers can still affect the skew of a graph. Let's take a look at some examples. I'm going to make up some histograms that might be skewed in a certain direction. A histogram that would be skewed left would have some data values that are much, much lower than average. These very small data values would be factored into the mean when we're summing everything up and would bring the average way down. They don't actually affect the median very much, however. If we removed, for example, 10 very low data values, then the median would move up a little bit, but the other data values are very close together, so it wouldn't change much, whereas removing 10 very low data values would change the mean a lot. You can think of this as the tail of the graph. And you can remember that a graph is skewed in the direction of its tail. Therefore, a graph that would be skewed right would have a bunch of extremely high data values. with its tail on the other side. A graph that has no skew would be perfectly balanced, as all graphs should be. No tail in either direction, or alternatively, you might say two equally balanced tails. There's not any more particularly high values than there are particularly low values. On both sides, we have balanced graphs and balanced data values. If the graph isn't perfectly symmetric, then it would be maybe a little bit skewed left or a little bit skewed right. But if the mean and median are very, very close together, then we might say that the skew is insignificant. Even though it's technically skewed left or right, it's not enough of a skew that we would take note of it. And we'll talk more later on about what that would mean in terms of looking at a data set and painting a clear picture. The final thing we want to talk about today is measures of spread. Spread tells us how a data set is spaced out. If I know that the center of my data is 300, for example, that might mean that my data is between 297 and 303, or it might mean that my data is between 50 and 1,000. My data could be very spread out or very close together, and the mean, the median, the mode, none of these things tell us about the spread of my data. And so we need other heuristics for this. We've talked already about the range and the IQR, which are two simple to calculate measures of spread. They are straightforward, and a box plot does give us a nice picture of a graph. But the most powerful measure of spread that we're going to discuss in this class is called the standard deviation. And what the standard deviation does is it measures for every data value the distance from the mean. We will then, for reasons we won't discuss in this course, add all of those, square all of those differences and add them all up. Then we will divide by the number of data values minus 1 in the case of a sample. And then we will finally take the square root. Now, there are a lot of little bits and pieces as to where this formula comes from, and I don't want you to concern yourself with them. We will want to know how this formula works, but mostly we're going to want to talk about, which we'll go into more detail for the next exam, what this number means. Let's first break down the pieces of this formula. Let's talk about what we can interpret it with, and then we'll talk about how to find it through example. So this right here, which is pronounced sigma, is the standard deviation. Sometimes we may talk about sigma squared, which would be the variance and would simply remove the square root on the other side. But standard deviation ends up being a more useful measurement. So we'll work with that one. Little x, as we mentioned before, represents the data value, and x with a bar over it represents the mean of the data set. A lowercase n, we know, represents the sample size, and if we were working with the whole population rather than a sample, we would take a capital N. Also, once again, for reasons we won't discuss in this class, if we were working with the whole population, we would divide by n rather than n minus 1. Very briefly, the reason that we do this is because if we know the whole population, then there's no question if our data is correct, so we don't have to account for any uncertainty. Whereas when we're working with the sample, we know we're missing some stuff, and so we divide by one fewer to allow for a greater amount of uncertainty. But we won't talk about exactly why that choice was made in any more detail in this course. What we will do is we'll go through an example. So let's take a look here. 10 students responded to a survey reporting how many hours each week they spend on their phone. And we want to find the standard deviation for this data set. 1, 1, 2, 4, 6, 6, 7, 9, 12, and 15. The first thing we need to do is we need to find the mean, which we know we can take by adding up all of the data values and dividing by the number, which is n equals 10. 1, 1, 2, 4, 6, 6, 7, 9, 12, 15 adds up to 63 divided by 10, or 6.3. Next, we're going to need to make a table to keep track of our information. You can do this using Excel in order to make your job a little bit easier. If your data set is particularly large, I would strongly recommend it. For a data set this small, it's not too difficult to do by hand. The first thing we'll do is we'll list out each data value. 1, 1, 2, 4, 6, 6, 7, 9, 12, 15. Next, for each data value, we will need to find the difference from the mean. So here, the difference between 1 and the mean will be -9. -9, -8, -6, -4, -4, -3. Whoops, I don't know why I decided that the mean was 10 here. That's not our mean. We calculated our mean to be 6.3, so that's what we'll use. 10 is the sample size, and that's not what we want to use here. So for example, 1 is -5.3 below. -5.3, -4.3, -2.3, -0.3, -0.3. Then I've got 0.7, 2.7, 5.7, and 8.7. Next, we'll need to take this value and square it. Here, we'll definitely need to pull out our calculator. So 5.3 squared gives us 28.09. 4.3 squared gives us 18.49. And we'll go through each data value in turn. So 5.29, 0.09, 0.49, 7.29, 32.49, and 75.69. Next, we'll need to add all of these values up. So we'll add all of these values together. 28.09, plus 28.09, plus 18.49, plus 5.29, plus 0.09, plus 0.09, plus 0.49, plus 7.29, plus 32.49, plus 75.69. Gives us 196.1. This would be, we can write out in more detail the notation, the sum of the data minus the mean squared. We squared each individual data value before adding them up, rather than summing them up all before we squared. Because we're taking the average with the mean, if we did add them all up before we squared the number, we would have ended up getting 0, which is why we need to square them first. Otherwise, we would just get 0 every time, and this would be a very worthless method. The next thing we'll find is the variance, which we'll call is sigma squared, which is where we take this sum we got above and divide by n minus 1. So in this case, we need to take the 196.1 and divide by 9, which will give us 21.788. 3 decimal places should be plenty here, I think. And finally, we'll find the standard variation, which is bound by taking this entire value and taking the square root. Which will give us 4.668. Now, what does this number mean? We're going to talk in more detail a couple chapters down the road about interpreting this number with higher precision. But for now, all we need to know is that a larger standard deviation means the data is more spread out, whereas a smaller standard deviation means that the data is less spread out, more concentrated. That's all we've got for today. See you guys next time.